Yes, sir. Alhamdulillah, fine.
Did you get your earlier semester grades for some subjects?
Yes, sir.
Yes, sir.
Okay. How are they? Good?
Alhamdulillah.
Alhamdulillah, sir.
Okay, very good. So we have to say Alhamdulillah always, okay? Alhamdulillah ala kulli hal. Whatever may be the state, okay? We have to express the gratitude to Almighty.
Yes, sir.
Yes, sir.
Actually, what is our plan today? We have completed our integration and differentiation. Now we are at a place where we have to deal with a very important topic in engineering, the solution of differential equation numerically. As always, you know that not always we need numerical technique to solve our differential equation. We have our analytical method already learned. Didn't you learn differential equation in your mathematics course?
Yes, sir.
Yes, sir.
Okay. Then you know how to deal with. So before going to the mathematics, actually, we have to relate our understanding with our subjects. Then we can proceed with solving our equations from the practical point of view. Otherwise, things will be very abstract to us. Okay. There exist many techniques, actually, many forms of differential equation exist. In this fundamental course, we will be introducing such differential equations that are frequently occurring in your learning in the undergraduate level. For example, you have seen differential equation in your electrical circuit, didn't you?
Yes, sir.
Okay, in transient analysis, you have seen it, okay? And you see differential equation in this semester in your electromagnetics course. One thing I have been informed that in the mid-exam, some of you have copied and your teacher probably detected them, and it will be very dangerous for you if you are detected that some of you have been copied, okay? The thing is that those who are copying, they do not know actually the correct answer. For this reason, what it is happening that the error is become replicating. Okay, it is very uncommon that a few students would have same mistake. Don't you think so?
Yes, sir.
So I have instructed the teacher to set the mark of all those copies equal to 0. No matter where he is a good student or bad student, some good students are also helping those guys, okay? Those are depending on copies. So all are will be equally punished. Unfortunately, those could not be detected at the time of exam. If then your semester will be cancelled, something like this. So be careful about that. I am warning you from the very beginning that do not do this thing. As we cannot see you on the other hand totally. We are just relying on your integrity. Okay, learning and teaching process cannot be based on unfair means. Knowledge cannot be gathered unfairly. Okay, be careful about that. So do not contaminate the sacred relationship between your teacher and you with some nonsense things. Okay, that is not good. Okay, let us start with. Actually, okay, in this point, I will be asking you a few questions from your earlier learning. Okay, in your MATLAB, have you ever solved differential equation by using MATLAB?
No, sir. So far, not.
Not. Okay, have you done not? But actually, I was planning to give you an introduction Let me discuss something about it. Then we will discuss. I will give some introduction how to use MATLAB in solving a differential equation. The thing is that in MATLAB, you see many routines are there already built. You can use them to solve your problem. But it is very important for us to write our program by ourselves using the simpler algorithm that we are learning here. Then you will understand how some simpler problem you can easily solve by your own by writing your own codes. In order to write the codes, actually, we have to know how to translate our differential equation into a form that will contain some addition and multiplication. At the beginning of this course, in chapter 1, we discuss about modeling, isn't it? If you have an engineering problem, you have to model the problem mathematically first, isn't it?
Yes, sir.
Once your mathematical models are available with you, then you can solve it either by analytically or by numerically, okay? So let us start with the problem, how to derive the differential equation first. Okay, sometimes you say that we are taking problem from electrical circuit, but I think that everything that I discussed, particularly in my class, was taken from examples were taken from your earlier learning. Nothing new was there. So if you have your problem given, then from that problem, you can derive your differential equation by your own, describing the scenario there in your problem. Then in solving your differential equation, then you can apply your analytical technique there or numerical technique there to solve them, okay? Let us start with the problem. You see, we have our two classes of differential equation. You see that when differential equation will be, we are solving, then you know that this is some form of integration, isn't it? So when you are integrating, then some integration constant will also always be associated with the solution, isn't it?
Yes, sir.
Then those integration constant can be determined from what? The initial conditions, isn't it? Sometimes if your problem is initial value problem, then we can find the initial values. Either initial values will be given to you, or you have your problem from which you have to extract the initial values. And another class of the problem that deals with differential coefficient in a space that you will find in your electromagnetic course, where you will see that your physical quantities are distributed in the space, or it is being propagated from one place to another. In such cases, you need your differential equation to know the behavior of these physical quantities. In the electromagnetics, it will be electric field, magnetic field, charge, something like this. Then what will happen in such cases, you will find differential equation where a space will be involved. If your space is there involved, then your space should have boundary, isn't it?
Yes, sir.
So in most of the cases, your space will have boundary because we are dealing with finite space. If your space is infinite, sometimes we call it free space. In such cases, your space can be that whole inverse, where boundary is not there. But in all practical problems, we will have our finite boundary. If we have our boundaries there, then we need to know the condition of the physical quantities when they are reaching at the boundary. So in such cases, some integration constant will be available. Those constants should be determined from the boundary values, okay? So in such cases, actually we can broadly categorize our differential equation into two broad categories. One is the initial value problem. Another class is?
Boundary value.
Another class is boundary value problem. Okay, good. So if we have our initial value problem and boundary value problem, then we can proceed with solving by using any one of the techniques you have learned so far, or we can use our numerical technique that we are going to learn from this point ahead. So let me start with a simple problem. Then we will be discussing the content with this book. So you see that your integration is the process of solving the differential equation. In such cases, what will happen? you'll have some value, given initial values. Okay, you have to know actually the physical meaning of the initial values. Can you tell me what is the meaning of the physical meaning of initial values? What do you mean by actually initial value that is in your system?
Sir, actually, differential equation. After solving differential equation, we are getting a function, right? And that point satisfies that function. That's the initial point or initial value.
Yes, that might be initial values, but I am asking you the question from where those initial value actually coming physically. This is my
From
question.
experiment, actually. From experiment, there is a point. I think.
Actually, the thing is that not always your system may contain initial values. Practically, initial values means something is retained in your system before your present activity begins. For example, say you are in the third year. When your teacher is teaching some third year courses, you should have some knowledge of your previous learning, isn't it? Can
Yes, sir.
anyone enter in the first year, can start a third year course?
No, sir.
No.
Generally not. That they not happen. That means you are assuming that the students should have some prerequisite learning from their previous years. Based on that learning, we will be just augmenting our learning of the current semester. So those learning that you have already learned in the earlier semester can be thought as some initial values with you. Then those initial values, on top of the initial values, we will be building our solution in the current semester, isn't it? But if
Yes.
your initial value is not there, then your system is sometimes we call a relaxed type. And for example, if someone is there, unfortunately, although he is in the third year, but he has forgotten everything, what was there in the past. In such cases, what will happen? Although he can learn, but his initial values are set to 0 initially. The reason is that he has forgotten everything. Actually, the thing is that when the initial value exists in a system, you have to know this thing first. Okay, in your next semester, you will learn a course, and hopefully, I will be teaching it, inshallah. The name of the course is Signals and System, one of the basic courses of electrical engineering and very important for your further progression. That thing is, we'll be discussing much about those things there. But at this outset, we can also discuss a bit about it. For example, this is one example, okay? That means if your system has the property so that it can retain the value of its previous state, we call it a state. For example, when you are in the second year, you had a state. Now, when you are promoting to third year, you are simply going to another state. That means a state change is occurring at a time. That present state will be examined, or your present state will be modeled. That will contain your previous learning. This is a very general example. Another example can be something like this. Say you are depositing money in your bank. Okay, at the end of the year, for example, you will have a balance in your account, isn't it? Then in the next year, when you are depositing something, then your balance will be equal to what? What was there previously in your account, that will be added with your present deposit, isn't it?
Yes,
Yes, sir.
That will give you your money. But if your deposit is 0, then still your bank will deposit it, but that deposit amount will be the current deposit, okay? If you go in this way, there exist many examples in your practical life where some initial values of the previous states are very important in order to consider the present state or future state. Generally, it is believed, generally what it happens, that if you have your system, that system can retain something in it. That retention is coming from the previous state. That signifies that your system must have memory, isn't it?
Yes, sir.
That memory is very general term. For example, in our practical electrical engineering subject, where we deal with our inductor, we deal with capacitor, we deal with resistor, some other active elements such as operational amplifier, a transistor, a MOSFET, or some other elements can be there, okay? Let us consider first the passive elements, okay? What is the characteristic of a resistor? Resistor characteristic is something like this. If you apply a voltage there, then a current will be flowing through the resistor, isn't it?
Yes, sir.
Yes, sir.
And if we switch off the voltage, will there be any current?
No, sir.
No. Good. Now consider you have an inductor. You apply a voltage across an inductor, your inductor will be carrying current. If you switch off your inductor, will the current will be zero?
No,
No,
sir.
Yes, instantaneously?
No, sir.
No, sir.
Inductor will off the change of current.
Okay. Similarly, if you have a capacitor, similar situation can be there in terms of voltage or current, isn't it? That means that your inductance actually has a property that voltage drop across the inductor is dependent on what? You see that if we have a resistor R, your voltage across the resistor is simply I multiplied by R, isn't it? If we have an inductor, voltage across the inductor is rate of change of your current, isn't it?
Yes.
And if we have a capacitor, current
Yes,
through
sir.
your capacitor is the rate of change of voltage, isn't it?
Yes, sir.
Yes.
So where there exists a rate of change,
Yes.
this is very similar to what? If we have a mass, consider that that mass is placed on a surface, that surface is frictionless. If it is frictionless, if we apply a force there, F, then what will happen? From the rest position, your mass will begin to move, isn't it?
Yes, sir.
Then
Yes,
if you
sir.
want to relate those things, what we can do, it will attain a velocity, for example, say. As your x is there, then a velocity will be there. Then you know the relationship from your Newton's second law that F is equal to ma, isn't it?
Yes, sir.
Yes, sir.
It is equal to what? M into rate of change of velocity, isn't it?
Yes, sir.
So mathematically,
Yes, sir.
you see all these three equations are not they mathematically same?
Yes, sir.
Yes, sir. Same.
Actually, this signifies that whenever you are placing a mass,
Yes, sir.
then your mass actually will not attain the velocity quickly. It will have some rate of change of velocity there in order to have the thing, okay, this is not the thing. Now the question comes, whenever a rate of change is there, that rate of change actually is a sluggish term. That means it is simply giving you a, what we call an inertia-like behavior in your system. Otherwise, that derivative will not be there, okay? So, and even you see that whenever your mass is accelerating, it will store energy in it. That energy is half mv square. You know this thing, isn't it?
Yes, sir.
Yes, sir.
So what is the
Kinetic
kinetic energy of a mass?
Half mv square.
So what is the energy associated with an inductor?
Half Li square.
Half Li square. What is the energy associated with a capacitor?
Q.
Half Cv square, isn't it?
Yes, sir.
Yes, sir.
So All are not they looking same? Now the question comes. Say at one stage you are withdrawing the force. Then where this energy will go? That energy will be remaining stored in your mass, isn't it?
Yes, sir.
Yes.
Similarly, whenever you are withdrawing your voltage, this energy will be stored in your inductor. And that energy will also be stored in your capacitor. Okay. So the thing is that whenever, for example, again you are applying and consider that your inductor, capacitor, and your mass are ideal. No loss is occurring there. Then after withdrawing your current or voltage, you are having this energy already there in your system. Now, if you again reapply your sources there, what will happen then? Again, your inductor, capacitor, or your mass will begin to store energy, isn't it?
Yes, sir.
On top of what? On top of
Remaining.
the energy that was there initially present, isn't it?
Yes, sir.
So this is actually the thing that will be occurring in our system. When your system has some form of memory, that means it can store some information, some energy in it that was present previously in previous activities. Later, when we again begin another activity, then those conditions should be borrowed to the next state. Otherwise, your modeling will not be correct. Okay. But for the register, that will not happen. The reason is that whenever you are withdrawing your source, your register cannot store energy. It is a memoryless element. Okay. So whenever we are dealing with differential equation, you have to consider that your circuit at least contain one energy storage element. Okay. There may be more, but at least one, isn't it? Otherwise, your model equation will be algebraic type. So a resistive network purely will give you algebraic equation, and your inductive network generally will give you differential equation, but that differential equation we will see later that, and you have already seen in your electrical circuit transient course that when an inductor is there in your circuit, it can, that the quantity will be modeled by differential equation, but that solution of your differential equation will contain two parts. One part where your rate of change of your variable exists, in other part, either it will be repeating or remaining constant. As a result, you can separate your quantity into two domains. One is called transient state, another is called steady state. Have you learned about it?
Yes, sir.
Yes, sir.
So your differential equation will be valid for transient state. For example, say, if we have an inductive circuit, there is one of the good example that we always give, and this is the ideal example for a electrical, in order to start with differential equation for electrical engineering. You know that if you apply Kirchhoff's voltage law there your equation equal to what? L di by dt plus Ri is equal to E, isn't it?
Yes, sir.
Or you can simplify di by dt plus R divided by Li is equal to E by L.
Yes, sir.
We have discussed this thing earlier. Not always that your circuit will be something like this. You can also use Thevenin equivalent there to do that. Okay, we'll discuss the thing later. So now the thing is that if we have this thing with us, is it not an ODE, ordinary differential equation?
Yes, sir.
And it is a first order differential equation, isn't it? Because the highest derivative exists in your differential equation has a derivative order of equal to 1. Now you know how to solve it, isn't it? If we know how to solve it, then that solution you have already obtained from your classical technique. In the classical technique, how did you solve that equation? We can solve this equation classically by using a technique that can separate your solution into two parts. One is called complementary function, another is called particular integral, isn't it?
Yes, sir.
this is what your simple review of your differential equation, okay, isn't it? Your particular solution is actually how to find this complementary. Complementary solution has another name. It is also called homogeneous solution, isn't it?
Yes, sir.
Okay, now the question comes then, when any differential equation is called homogeneous, when the source term of your differential equation equal to 0.
Yes, sir.
Okay, that means if we write our equation in this way, we are now calling the current I is the homogeneous solution R by L I H is equal to 0. This is the homogeneous part of your solution. Okay, from that homogeneous solution, you will find your I is. Then you have to have some technique to calculate your IP, the particular. Then your total solution will be equal to IH plus IP, isn't it?
Yes, sir.
Now tell me, how can you solve for IH? One of the solution technique is simple, okay? We know that if we do not have a source in our system, then the solution will take this form, e to the power some lambda t type. This is what the general solution we can assume for IH, that your IH will take this form. If we have our homogeneous linear OD is there and homogeneous solution.
Sir, in the general form, is there any term m associated at front? A e to the power lambda
This
t.
form. If we have this form, anything could be there, okay? It can be m or whatever the thing you put there, this will be a characteristic constant. This doesn't matter in what ways you are designating it, okay? Then your solution is this, okay? If we assume that our solution is e to the power mt form, then it will be something like this. So there is no any difference between assuming the solution e to the power lambda t or e to the power mt, okay? The thing is that your solution will take this form, okay? You can assign another constant there of your choice. So if this is the case, this is your solution, we are assuming that our solution will have this form, then that solution must satisfy your equation, isn't it?
Yes, sir.
If we want to put that solution there, e to the power lambda t plus r into e to the power lambda t would be equal to 0. Then this will be equal to what? Lambda e to the power lambda t plus e to the power lambda t equal to 0. Our objective is what? We do not know anything about lambda or m, whatever it may be. But this equation says that e to the power lambda t cannot be equal to 0. But the reason is that we assume that solution it cannot be equal to 0. Then in order to satisfy this equation, then lambda plus r by L. R by L. This should be R by L, okay? So lambda plus R by L would be equal to 0. Then your lambda would be equal to what? Minus R divided by L. So if your lambda would be equal to minus R divided by L, then your solution can be written as generally a constant A into e to the power minus R divided by LT, isn't it?
Yes, sir.
That is what your homogeneous solution. Then how to find the particular solution? Yes. Hey, I am not asking you new thing, okay? In the last class, I said that before coming to this, joining to this class, you have to revisit your differential equation in math. How many of you have done it? If you do not follow, for example, what your teacher is suggesting you, then learning will never be important to you, or you will not feel the joy of learning, okay? There exist many techniques of finding the solution for your particular integral. One of the technique is called method of undetermined coefficient. Have you heard about this term? We also use this term in our integral course also in this course. In your differential equation course, did you just hear this thing?
Yes, sir. There was a particular.
Yes, sir. It was in 1-1, sir.
C1, C2, and C3, different kind of undetermined coefficients. So there we used initial conditions to find the values of those constants.
This is not something like this. Actually, the thing is that we have, for example, a source term in your differential equation, or sometimes called forcing function. That forcing function is actually giving you the output of the present state. If we have a source term there, then that source term will, okay, then the thing is that, okay, physically you consider the thing first. Your circuit was something like this. We are saying that if we want to find the current, that current will have two contributions. One is the homogeneous part, another is your particular. Your particular solution will be coming from this source. Now the thing is that that solution is actually the your total current I, the contribution of I, contribution to I due to that forcing function of the source will follow the same nature of each source. What does it mean? It means that if we give a source, that source is a constant E, because we are giving a source that is a step function, something like this. At time t equal to 0, we applied this force there in our circuit. Then we are finding the solution t is greater than equal to 0. In this case, what happened? But if we are in this region, then our source is constant. If our source is constant, we are saying that that constant source will contribute to the output, and that will also be a constant. So if we have a constant E in our input or forcing function, then that will give you an output. You can consider that output or the particular solution IP equal to K, a constant. This is what your undetermined constant, you do not know yet, but you know the behavior, okay? There exists some restrictions of applying this technique. The restriction is what? Like Thevenin's theorem. If we have our system that is linear and time invariant, that system will obey this principle of undetermined coefficient strictly. So what is happening then? The general conception is what? If your source term has some behavior with respect to independent variable, then that behavior will be translated into the particular solution. If it is a function of time, then it will also be a function of time. That function of time can be exponential type, can be sinusoidal type, can be other polynomial type, whatever it may be. So that will be replicated, that this time stamp will be, or time profile will be replicated in your particular solution. In our case, our input E is time is constant. That will give you a constant particular integral. That constant you need to determine, okay? If you want, then what is happening then? Any part of your solution, IAs or IP, both will satisfy your differential equation because both are the solution of the differential equation. So in our case, our forcing function is constant. That will give you your particular solution that will also be a constant. That constant we have to determine, okay? That constant we have to determine what is the value of this constant. How to do that? You apply your particular solution to your differential equation that you had originally with you. This is what our differential equation. Then for particular type solution, that solution will satisfy this equation. Then we said that if we have our E that is constant, that will give you a particular integral that is also a constant. Then you put this, apply this solution to your differential equation. Then it will be equal to a d dt k plus r divided by lk is equal to E by L. And you know that this term would be equal to 0 as your k is independent of time. As a result, not changing with time. Then you will have this thing there, R divided by LE is equal to E divided by L, R divided by RK. Then K is equal to what? Is it not K equal to E divided by R? Is it
Yes.
okay?
Yes, sir.
Yes.
Then your total solution I is equal to IP plus IH. You determined your IH as A to the power minus R divided by LT. Now you found your particular solution is equal to E by R. Okay, once this solution is available to you, in this solution, this constant is not known to you. Is it known to you?
No, sir.
That constant is actually coming from the initial conditions of your system. Now the thing is that generally what will happen, if your inductor is carrying a current, for example, say for time t is less than 0, your inductor was carrying a current equal to say IL0. This is what the current flowing through your inductor before application of the source E. And you know that your inductor has a behavior something like this, dL by dt. If we have a system that contains a derivative, can this derivative be current equal to 0, then this value will be equal to infinity, isn't it?
Yes, sir.
Yes, sir.
You must know it from your electrical circuit behavior of an inductor. So an inductor actually cannot change its current instantaneously. For this reason, when an inductor is carrying a current IL0 and you just apply a source there E, at time t equal to 0, this current will be existing there in your system inductor, because inductor cannot change the current instantaneously. As a result, you apply 2 times there, you know it from your transient state. One is called 0 plus, another is called 0 minus. Have you heard this 2 designation of current earlier?
Yes, sir.
Yes, sir.
Yes, sir.
What is it? It is simply just immediate before changing the
0.
state. And this is what the immediate after changing the state. The difference between 0 plus and 0 minus is actually 0. But the state are different. Okay, it is there that T minus actually what current we are equal to 0 minus, and that is equal to your IL0. Now, if we have our time t equal to 0 plus, this current will remaining the same. The reason is that inductive circuit cannot change current instantaneously. So if this is the case, then we have our current I equal to A e to the power minus R by LT plus E by R. At time t equal to 0, your current I equal to IL0 is equal to then A plus E divided by R. So your A equal to what? IL0 minus E divided by R, isn't it?
Yes, sir.
Then if you apply this thing there in your I, that I equal to then what is that? IL0 minus E divided by R plus E to the power minus R divided by LT plus E divided by R. Okay, you can group your term in such a way that, can we write the thing in this way? Okay, E divided by R plus IL0 minus E by R, E to the power minus R by LT. Okay, when your T is tending to infinity, what will be the value of I?
E by
Is
R.
it not equal to E by R? So what interesting thing we are obtaining from here? Actually, this is nothing but our particular solution. So your particular solution is actually giving you a value, we call it steady state value. Isn't it?
Yes, sir.
And sometimes this current is called I infinity. So in general, in many of your texts probably for this type of circuit, you have learned this thing IT is equal to I infinity plus I0 minus I infinity into e to the power minus R divided by LT. Haven't you seen this equation in your text of electrical circuit?
Yes, sir.
Yes, sir.
So this is what the solution, okay? Now the question is, in this case, your I0, today I will just recap your thing, okay? Your I0 is actually the value of your inductive current that is coming from the previous step. In this simple example, it has been said that the value is already given to you, okay? But if your value is not given to you, then what will happen? You must have your circuit given to you. That from that circuit, your state will be described, and you have to find the value of your initial value for your next state from the behavior of your circuit. Okay. Consider that a network something like this. I have taken this from your Arvind's book. Okay. Consider that this is your position 1, this is position 2 of your circuit switch. And initially, your switch was there at this position 1 for a long time. And at time t equal to 0, your switch was placed at position 2. And you have been asked to calculate the output voltage across your 6 ohm resistor for time t is greater than or equal to 0. In this problem, your differential equation is not there. You have to derive it, number 1. For which time you need to find your differential equation? When, because at time t is less than 0, your circuit was at steady state. And these are the DC voltages, isn't it? Are not they?
Yes, sir.
Yes, sir.
If your circuit was at steady state for time t is less than 0, that in that case, what is happening there in your circuit? Or can you just represent your circuit when time t is greater than less than 0? Time t is that less than 0, the existence of this source is actually no meaning because it was not connected, isn't it?
Yes, sir.
And at that time, what was the behavior of the inductor? Because steady state there, then you, in the steady state, if your circuit is DC, how your inductor behaves?
Short circuit.
It will be behaving like a short circuit, isn't it? Dead short. Okay, from this analysis, can't you find the current flowing through your inductor and the voltage V they are present? Tell me, what is the current flowing through your inductor? How to find it?
LDI by dt.
Integrating VL.
Integrating VL, your integration will be applied for steady state. It is short circuit, dead short. A circuit is there, although it is inductor, but it will be behaving like a wire, like something like this. Then this is a simple two-loop network. A student of first year can solve it. Consider that this current is your IA, I1, this current flowing through this circuit is I2. Can you solve this network for I1 and I2?
Yes, sir.
Yes, sir.
Then your first loop will give you what? Minus 36, and this resistance is equal to say 2 ohm.
2
Then
I1
plus 2
36 plus 6 into I1 minus 4 into I2 is equal to 0. This is equation 1, isn't it?
Yes, sir.
Yes, sir.
Then your equation 2 equal to what? Minus 2 into IA plus 4 into I2 minus IA, I1 plus 6 into I2 is equal to 0, isn't it?
Yes, sir.
Then you do not know that you have to replace the value of IA. Where is IA?
So minus I2.
IA is indicated there, okay? Your IA is flowing through downward through 4 ohm resistance. Then it is IA is simply equal to I1 minus I2, isn't it?
Yes, sir.
So you replace your I1 by I1 minus I2. Then you have to solve for what?
I1 or I2. These two.
Why do you need I1? Because we need to know the, yes, I1, I2 may be needed. Okay, you solve for I1 and I2. Once you have your I1 and I2 available, then your I2 is equal to your inductance current IL0 minus. And when your I2 will be available, then I2 minus 6 ohm would be equal to your V0, 0 minus, isn't it?
Yes, sir.
These are the voltages remaining in the steady state. But now our circuit is what? Now you have to consider your circuit for time t is greater than equal to 0 when switching occurs. In such cases, what happened? A source, a source was a source was there. What was the value? Probably 12 volt. Then your switch is transferred in this position. If your switch is transferred, you don't have this thing with us. There is no any meaning of the existence of this source. Is there any meaning?
No, sir.
No, sir.
No. Now, can we consider our inductor short now?
No, sir.
So our inductor is again in the state. So you have to draw your inductor again that your network will be equal to an inductor there is 6 ohm resistance or something like this. Okay, is it not that circuit? You got the point? Okay, now the question comes. In order to solve this circuit, what you need to do? Because this circuit contains an inductor, your switching occurs at time t equal to 0 ahead. What you can do? Just at the beginning of my lecture of this course, I said that if you have a linear network, we can easily transfer and that contains, for example, an energy storage element. Then what we can do? The network can be reduced into a form. That form will contain a Thevenin resistance and a Thevenin voltage, and your the inductance that you have connected. Then it will become a simple RL circuit, something like this. So if you want to do that, what you need to do? First step is what?
Removing the.
You have to remove the inductor, isn't it?
Yes, sir.
If we remove the inductor, this is what the inductor position. Okay, 6 ohm was there. Then what we need to do now? You have to find your VTH and RTH.
Yes, sir.
Now tell me, this is a circuit that contains what? a dependent
Control.
source as well as an
Independent source. Yes.
independent source. If a network will be containing the dependent source and independent source, how to find the Thevenin equivalent?
So for the Thevenin voltage, I will conduct nodal analysis and find the voltage there. And for Thevenin, for the Thevenin resistance, I need to. There are two processes. First, short circuit current. First process is finding the short circuit current, and by whole dividing it V is equal to IR, applying V is equal to IR. And the second is second approach is applying 1 ampere of current on that node and finding the voltage across that.
Okay, very good.
Yes, sir.
Actually, the thing is that as your network contains a dependence, so I don't know how many of you actually memorized it or learned it. Very simple. The thing is that as your source contains a dependent source, Thevenin actually voltage calculation is not that is very easy, but Thevenin resistance calculation is a bit difficult. But you can apply your general principle there. Actually, the thing is that if we open this two terminal, then no inductance is there. Then what is the voltage looking from this side? Is it not equal to VTH? So we call our VTH is equal to VOC, open circuit voltage, isn't it?
Yes, sir.
Yes,
And
sir.
that open circuit voltage is the voltage looking from this open terminal, isn't it?
Yes, sir.
In this case, you see that no current is flowing through this branch,
Yes, sir.
but a current is flowing through this branch. What is the current?
That will be 3 ampere.
Okay, good. This will be 3 ampere. If this is 3 ampere, what will be the voltage here? Isn't it?
Yes, sir.
Okay, fine. Then if we want to find the VTH, VOC with this polarity, plus minus, this is your VOC. Then can we traverse the loop in this way, virtual loop?
Yes, sir. We can.
If we start from this point, it's VOC
Yes, sir. Yes, sir.
minus 6 volt, then voltage across these two terminal is nothing but 12 volt, minus 12 is equal to 0. So your VOC equal to what? 18 volt, is it not?
Yes, sir.
Yes, sir.
So your 18 volts. Now the next question is what?
Thevenin resistance.
Thevenin resistance. Okay, if you want to find the Thevenin resistance, what to do?
Sir,
Short circuit the
and
source.
Actually, two technique that already the student was talking about. Okay, we can apply a test source there, then find the current. Okay, or when we are applying a test source, be careful about that. Independent source must be deactivated. Otherwise, it will not work. So what will happen? The general process is what? You short circuit this two terminal, keeping everything in your network as they are. So if we short circuit this two terminal, what will happen? This is what moves I can. Is it not this circuit?
Yes, sir.
Okay, fine. If this is your circuit, then can you find your short circuit current ISC?
yes, sir. We need to solve the equation again.
One node analysis.
One node analysis, I think, will work. Yes.
Do you need node analysis there? Which analysis is more easier for this case, node or loop?
Loop, sir, because we need to find out the current.
This is what the problem. Sometimes you confuse about your node analysis and loop analysis. For this reason, what I have observed there in your NEET exam, okay, a simple problem was there. You considered it as I said that we apply your node analysis. You just applied what? Loop analysis. Okay, then it took longer time. Even they could not arrive at the solution. For a home.
Sir,
Actually, this is one of the important measurement of learning is also prudently applying the rule. Okay, you can have your classical thing there, but This is not engineering. Engineering is something that you have to apply your knowledge very efficiently in terms of time, in particular, and the solution. Now, thing is that, okay, you can apply your loop analysis there, like your previous case. This loop current is say I2. This is your I1.
It's pretty straightforward.
Then what you have to do, minus 12 plus 4 into I1 minus I2 is equal to what? Is there any
Zero.
current
Zero,
involved
sir.
there? Equal to 0, isn't it? This is
Yes,
one
sir.
equation. Another equation is minus 2 into IA plus 4 into I2 minus I1 plus 6 into I2 equal to 0, isn't it?
Yes, sir.
Our intention is what? Solving I1 or I2?
I2.
I2, because your I2 is equal to ISC, isn't it?
Yes, sir.
Yes, sir.
So once your ISC is available, you can easily solve it. ISC is available, then your RTA should be equal to what? If ISC means if we short these two terminal, that current is your ISC. It is simply equal to VTH or equal to VOC divided by ISC, isn't it?
Yes, sir.
Fine. Then your RTH is available, your VTH is available. You have your circuit. Then you can directly put the, so if you are asked to calculate the voltage across the resistance, that was your output. Then once you have your current available, or what you can do, you can easily find the current flowing through your inductor, isn't it? And that current is also flowing through what? Your resistor, okay? Or you can have your own way to find your VOT, that is up to you. This depends on your electrical circuit solution from your first year. So in this way, actually, if you have your network will be given to you, then using that network, you can reduce the network into a simpler form. If your network will contain a single energy storage element, then you can either directly apply the solution, or you can derive the first order equation. You can solve it analytically. That's it. But in our course, we will be solving them analytically. This is what your first order differential equation. Okay. Now you can have your system something like this. If we just extend this problem by adding another energy storage element there in your network, say this network is a simple network excited by a DC source. We are calling it now UT. That means your source is there present from time t equal to 0 ahead. This is your R, this is your L, this is your C. You have been asked to calculate the voltage across VC. Can you derive the differential equation?
Yes, sir.
How to start with?
Sir, I will apply KVL across the loop.
Okay,
Minus
fine. If we apply your KVL, this should be equal to E for time t is greater than equal to 0. It is E plus Ri. Say this current is I.
and
Ri plus L di by dt plus Vc equal to 0, isn't it?
yes.
But can you solve this network? Because if you are have been asked to solve for Vc, then you have an I there. Then that I should be replaced, isn't it? How can we replace I?
Sir, VC, I'll write VC is equal to 1 by C integration of I dt, and then I will differentiate it again, so it will become a second order differential equation, and after that I'll solve it.
But in that case, your source term will be giving you, it would be equal to 0 if we differentiate it. Then that will not be representing your differential equation totally. It becomes an integral differential equation. Then you need, why we are going there? If we want to find, for example, VC, you know the relationship between current and voltage in C, and polarity is also given there. So your current through the capacitor is going in this direction. So what is that current? I equal to C dVC by dt, is it not?
Yes, sir.
Yes,
That's
sir.
And this is a series circuit. This is what the total current flowing through your circuit, isn't it?
Yes, sir.
Yes, sir.
Then you simply replace your I there in this equation. Then it will be equal to minus I plus RC di by dt plus LC D2I divided by DI2 plus VC equal to 0. If you want to reshape the equation in this way, that it will be equal to LC D2 VC DT2 plus RC dVC by dt plus VC is equal to E. Is it not the equation?
Yes,
Yes.
sir.
Yes, sir.
Fine. Then this is the, what is the type of the equation? Is it not a second order equation?
Yes, sir. Second
Yes, sir.
linear second order.
If you have a second order equation and you have been asked to solve for VC, then how to proceed with? Your equation is written as LC D2 VC DT2
Sir, at first solving, I will take the general form. A
just the same technique that you applied earlier, okay? A RC dVC by dt plus VC is equal to E, or you can divide by LC throughout, then it will be equal to dVC dt2 plus R divided by L dVC by dt plus VC divided by LC would be equal to E divided by LC. This is what your equation, okay? A second order ordinary differential equation. But like your earlier cases, your VC will have part. One is your VC homogeneous, another is VC particular. That you can separately determine. The homogeneous can be determined by setting this side equal to 0, then your solution will be equal to VCS. And we again, in the homogeneous type system, we know that our solution will be of this type. Then you apply this solution to your equation, then that equation will be equal to what? Lambda square e to the power lambda t plus R divided by L lambda e to the power lambda t plus 1 divided by LC e to the power lambda t would be equal to 0. Is it not?
Yes, sir.
And e to the power lambda t cannot be equal to 0, then you will have the equation R divided by L plus 1 divided by LC equal to 0. What is the name of the equation? Is it
characteristic
called the characteristic equation? And you see that in your first order case, you have your one root there in this equation. But in the second order case, how many roots will be there with us?
two roots.
What are these two roots? You can use your quadratic equation formula there. Okay, your lambda 1 or lambda 2, both root would be equal to minus b r divided by L plus minus square root of b square r square by L square minus 4ac divided by 2a. Isn't that?
Yes, sir.
And that is equal to what? Minus r divided by 2L plus minus a square root of can we take these two inside the root? Then it will be equal to r square divided by 4L square
Or yes, sir.
minus 1 divided by LC. Isn't that?
Yes, sir.
Yes, sir.
And you can also write this in this way, r divided by 2L plus minus square root of r divided by 2L square minus 1 divided by square root of LC square. Can you write this?
Yes, sir.
Then you see that you have your two roots there. If we have our two root, there our solution can be written as your VCA should be equal to some constant A into e to the power lambda 1t plus some constant b to the power lambda 2t. Okay, I am not putting the values of L only there, it will be very lengthy. Okay, this is determined. Then in second order equation, you see that you have your two constant to be determined. Now we have our particular solution VCB, and we can apply our method of undetermined coefficient there. You see that our source was E constant. then our solution VCP will also be a constant K. Then you put this solution to your equation, okay? D dt2 K plus R divided by L d dtk plus 1 divided by LCK is equal to E divided by LC, isn't that?
Yes, sir.
Then this will be equal to 0. This will also be equal to 0. 1 divided by LCK is equal to E divided by LC. So K equal to E, isn't that?
Yes, sir. Simple.
Then your total solution VC equal to e to the power lambda 1t plus B e to the power lambda 2t plus E. Okay, by putting the value of lambda 1 and lambda 2 there, you can obtain your solution there, okay? I hope you learn this thing. You consult with the electrical circuit book and find the nature of VC, okay? If the values of lambda 1, lambda 2 will be given to you, then you can easily calculate and plot the value. Consider that R is equal to, say, 2 ohm, L is equal to 1 Henry, C equal to 0.5 Farad, okay? Now it is your task now, putting this value there, you find your VC, plot it by using your MATLAB and learn how to do that, okay? This is the analytical technique, okay? We have to, now we are not discussing much about the analytical technique. We will be applying our, numerical technique there, okay? So if you want to go to the numerical technique, then again, we have to go to the text, okay? All this general description already made. Then you have to start, okay, these are the simple problem described. They are mechanical type. We will not be doing much about it. This is the analytical method. Just you can have a look there. Our study will begin from this part, okay? The Rangakutta method. Have you heard the name of this method earlier? No, probably.
No, sir.
Okay, fine. If not, but you have heard about at least this line. You have heard about this line in your first chapter. The new
Yes,
value
sir.
equal to old value plus slope into the step size. We named this method as
Euler's method.
Euler method, okay? So on top of this discussion that we made earlier in first chapter, okay, I am just assigning you to go further from this point ahead up to, for example, Euler method and this example, okay, and up to this method, okay. We will discuss about error analysis from the next class, inshallah. So this is a self-reading. This is a simple recap of what we have discussed in our first chapter, okay. That's it from my part today. Okay, I am planning to take a class test of mixture type, probably in the weekend, okay? So get prepared, your syllabus will be interpolation chapter 18, integration and differentiation. Okay, you are section A,
Yes, sir.
49.